Hi, this video will be presenting our work on a new generative 3D model for human feet, named FIND. I'm Oliver Boyne from the University of Cambridge. Reconstruction of human bodies has been extensively researched. Developing generative models capable of producing plausible humans has been a key area of this research. For specific body parts of interest, such as faces and hands, specific generative models have been developed using large volumes of high-quality data and careful construction. Meanwhile, the foot has been less explored. Recovering an accurate 3D model of the foot has significant applications in the shoewear and orthotics industries. Typical foot reconstruction pipelines produce 3D point clouds from depth sensors or use low-fidelity PCA generative models. These are not able to capture realistic reconstructed models, critical for ensuring accuracy. To address this, we produce FIND, our generative model, which is able to produce realistic, explicit meshes of feet with controllable pose, shape, and texture. Foot 3D, our dataset of high-resolution, scanned feet. A method for learning to disentangle shape and pose in an unsupervised manner. And finally, a method for learning part correspondences in an unsupervised manner. Our foot implicit neural deformation model, or FIND, begins with a template mesh. Next, for a given 3D point sampled on the surface of the mesh, our MLP network encodes this and passes it to two heads. The first concatenates it with a texture latent code, passing it through an MLP to predict the RGB value at that point on the surface. The second concatenates it with pose and shape latent codes to predict the necessary deformation at that point on the template mesh to match the target pose and shape. By sampling at sufficient points on the surface, we produce a deformed, textured, explicit mesh. We can alter the mesh and texture by changing the pose, shape, and texture codes. Our main training signal is a chamfer loss, a measure of the nearest neighbor vertex distance between two point clouds. We also use this as a metric for evaluating our model in 3D, in addition to a hand-labeled key point distance metric. Further to this, we evaluate our model with a 2D error metric by comparing intersection over union against ground truth scans for 2D renders over a range of camera angles. To be able to effectively model the foot's ability to articulate, our model must learn from the scans what geometry changes are due to subjects having differing foot shape and what geometry changes are due to articulation. To allow our network to learn this, we use a simple constraint. We know the identity of each foot in our dataset, so we can constrain our per-foot latent shape codes so that scans of the same foot must have the same shape. Here we show components of the learned shape space, capturing curvature of the foot and relative toe lengths, for example. And here is the learned pose space, showing a flexion and extension of the toes and a rotation of the ankle. It is also desirable for our model to ensure that the pose space it learns is meaningful. To do this, we take advantage of the pose descriptions included in our dataset and enforce a contrastive loss during training, encouraging poses with similar descriptions to lie close within the pose space, and poses with differing descriptions to spread out. An advantage of the implicit aspect of our model is that it allows us to produce outputs at variable resolution depending on the target application. For speed or memory critical applications, such as web or mobile applications, we can use a lower resolution template mesh to reduce the computational requirements. For higher resolution applications, we can use a higher resolution template mesh to produce higher quality outputs. To train our model, we produced Foot 3D, a dataset of 61 textured 3D scans of left feet from a variety of subjects in different poses. This dataset is available for download by the research community on our project page. We evaluate our model by comparing to two baseline models. The first, a PCA model constructed from our Foot 3D dataset, with vertex correspondences learned by training FoldingNet, a network to fold a 2D plane onto our scans. And the second, Super, a model released at ECCV this year to form part of a full body model. This model contains a rigged skeleton and models shape and pose. We show that the FIND model quantitatively outperforms our baselines according to our evaluation metrics of chamfer, or nearest neighbor vertex distance, 3D key point error, and intersection over union of 2D renders. Here we show the results of optimizing our model to fit the 3 validation scans compared to our baselines. We show the ability to capture the color on the mesh, as well as for significantly improved reconstruction quality, especially around the toes. A common use case for generative models is fitting them to real images. Optimization-based approaches often use image silhouettes and key points. We find that silhouettes do not provide sufficient information about the geometry of an object, especially for few view settings, and key points are too sparse for optimizing a model's surface. As a result, we introduce with our FIND model a new optimization loss based on foot parts, which is learned in an unsupervised manner. To do this, we first train a StyleGAN network to generate plausible renders of our 3D foot scans. Next, we train an encoder to encode foot scan renders into StyleGAN style codes. We then pass a render of a foot scan through this pipeline and observe a set of intermediate feature maps of the StyleGAN decoder. We notice that applying k-means clustering to these feature maps segments the foot into parts in a manner which is fairly multi-view consistent. To be able to use these foot parts as an optimization loss, 2 further elements are required. The first is to replace the k-means clustering stage with an MLP classifier trained on the k-means results, so that we can use this 2D part classification pipeline in a training loop. The second is to lift these 2D parts onto our FIND template mesh, so that we can use these parts with the FIND model. We do this by optimizing per vertex part probabilities so that, when projected onto 2D, they match the predicted 2D per pixel classes from our 2D pipeline. Bringing this together, we are now able to optimize the FIND model to images. First, we introduce a typical fitting pipeline. Given our parameters to optimize, which are shape, pose, and registration, we produce a predicted mesh, which we render using a differentiable renderer to produce a silhouette. We then compare this with our ground truth silhouette using an L2 silhouette loss. We then add a further training loss using our learned parts. We take our per vertex class probabilities learned on our template mesh and render these as class probability heat maps using our differentiable renderer. Next, we pass the ground truth RGB image through our 2D part prediction pipeline to give us ground truth part labels. Finally, we introduce a cross-entropy loss between these 2 representations of parts in 2D. We show here an example of this optimization process to renders of our 3D foot scans from 2 views. The rows show, from top to bottom, the ground truth and predicted RGB, the ground truth and predicted silhouettes and the overlap between them, the foot parts predicted by the 2D part prediction pipeline, and finally, the foot parts found by reprojecting the parts on the FIND template model. We show that adding our part-based loss during optimization quantitatively improves the quality of the fit, measured by chamfer and key point metrics. Here, we show the per vertex chamfer error for one example, showing that our part-based loss has allowed for more information to be extracted about the left side of the foot. as a silhouette-only approach cannot infer much about the geometry besides simply the outline of the foot. You can view our results, code, and dataset at our project page. We also have a web demo where you can view the Find model in your browser. Thank you for watching.